Hello, this is a video about DIY lithium-ion battery packs. I've kind of got a mini series going, so go ahead and maybe check out some other videos if you're looking for some more information. This video I'm going to talk specifically about cells in parallel and help you figure out, the watts and the amps and, what size fuses you should use and these types of things. So let's go ahead and get started. So real quick, I'd like to go over some basics. You're more than welcome to skip ahead. I've seen some questions and comments about people curious what they'll see these S or P or the C letters and they don't know what they mean. So real fast, the S is series and the P is parallel. So in this 3S 1P description up here, you have 3 batteries in series and they are 1 in parallel. So for instance, if I were to do this, then we would still have 3 in series, but now we would have 2 in parallel. So it's just a quick way to describe or technically describe, the design of your battery pack. Now, the more truthful statement here, which is why I have that 18S1P, is the more truthful description of this scenario, because each 12-volt lead-acid battery is actually a 6-cell battery pack. Not that you really need to know that, but that's why I put it here, is because that's actually how you should describe this. So the other one is C, and this is really important to what we're going to do today. So if you don't know what the C means, that you'll see some places, I don't know if there's actually a word for it. To me, it's just another descriptor like this S and this P. Oftentimes you'll see a battery and it'll have like a 1C charge or a 20C discharge. So to understand what that C means, you need to know what your batteries are. So if you have a battery that new was a 2200 milliamp hour, what I recommend doing is always just to convert to amp hours to make your life easier. And that battery in the data sheet or in the spec sheet or whatever, it says 1C charge. What that means is your battery can charge at 2.2 amp hours. Now, how do I know that? Because what the 1C means, it means like one capacity, if you will. So 2.2 amp hours is its capacity. We would times it by the C number, and then that'll give us 2.2 amps to charge. A little more confusing. So some batteries, like the high discharge batteries, they'll have like a 5C continuous discharge. So what does that mean? Well, in this situation, you would take, again, the capacity and you would times it by 5. And that would mean that the battery could do a, 8 or 11 amp continuous discharge. So that's what the C means. And it's really important for a lot of things because it's used all the time to describe, currents and amounts of power. Also on a very similar topic, if you're dealing with lithium ions, is you have energy and power cells. This is something I don't think a lot of people know about. And what that means is some cells are designed to either be used like in power tools or more designed for use in like flashlights. Or a grander or bigger example would be you could have a power wall or a large energy storage device, or you could have a electric bike or electric car, not really car, but like an electric bike would be a good example. And so an energy one would be a battery that has like a really high, like a 2200 milliamp hour battery would be an energy battery, and a power battery, generally they're the ones that are like 1500. But what you'll notice with these is energy batteries, sometimes in the description, they'll say like a 0.5C to 0.8C recommended charge and a recommended discharge of like 1C to 2C. And then on the power cell, it'll be something like 1 to 2 charge, and then discharge could be anywhere from like 5 to 20. And that's why the C number is really important, because when you start to figure out how to design your pack, you want to make sure you're well under or within these numbers. I know some of you, this number over here might be a surprise, but if you check the data sheet for your cells, they're usually fine with 1C. Most every battery can do 1C, but this 0.5 and 0.8, if you look, read down, it talks about longevity of your pack or your longevity of your cells. Generally, to get the most out of them, they like a little slower charge for energy cells. You know, power cells, they're not meant to last a long time. They're meant to be used and abused like in a power tool. And that's what they're designed for. Also, if you try to mix, it's generally not a good idea because there's a lot of things like internal resistances and other things of that nature that get involved. I'll do more advanced videos later that talk about those things and how you can kind of figure them out. But generally, either treat everything as an energy cell or just try not to mix. I mean, power cells can be used as an energy cell. They just, you won't have as much capacity. But if you're recycling or, doing things of that nature, you're using recycled cells, that's fine. Just treat them as energy cells. A lot of times, like the Powerwall guys and the RV and boat guys, they want an energy type cell because they want it to last a long time. So now let's start doing the math. All right, so now on to the math. I'm gonna do a little more common. I'm gonna change my scenario up a little bit. We're gonna do a 48 volt battery bank. So let's add an imaginary 12 volt battery here. And when I do the lithium math stuff, I'll say I have a 14S setup or project or battery pack. All right, so what we want to do is figure out what device you're using. Electric bike, RV, whatever. I'll do an inverter since it's a little more common, and we'll say a 2000 watt inverter. So the next thing, whatever item you're using, you want to find its peak draw. So inverters usually have a surge wattage, and for this one, we'll say his surge wattage is 3000 watts. So that'll be his surge. And then the next number you need to find or figure out is your lowest operating voltage. I did another video about voltages and figuring those out, but in a 48 volt system, usually it would be about 48 volts. You don't really want to drain lead acids much below 12. AGM lead acids don't like it at all. And if you're doing a 14 cell pack for lithium ion, that would be about 3.5 volts a cell, which is pretty good. Newer lithium ions actually don't like to go down much lower than that. Older coke based and the more common ones are, 3.2 is fine. But 3.5 is pretty good cutoff, especially for longevity. But that's too easy. So we'll do 3.2 volts per cell, so we'll say that's our cutoff. And so 14 times 3.2. So we're going to call our low voltage cutoff, our lowest operating voltage. We'll invent an acronym and call it LVO. That's going to be 44.8. So now we know the lowest voltage that the system is going to run at, and the maximum amount of wattage it's going to see. So the reason we wanted to know the lowest voltage is because when we go to figure out the amps for the fuses and stuff, the amp. So at 3000 watts, the amperage will be different depending on the voltage. The lower the voltage, the more amps that will be needed to reach that wattage number. At a higher voltage, you'll need less amps to reach that wattage number. So we want to know the most amount of amps so we can figure out the fuses and stuff and the amount of cells in parallel we'll need. So basically, it's real simple math. You just take your surge number and you divide it by your lowest operating voltage number. And that'll give us, I think, 67 amps. Now some of you are probably going to want to add in like inefficiencies, right? So we could take 3000 and, you want to add, let's assume 80% efficient. Most things nowadays are 90%, but, sense of caution, we'll side with caution, whatever, and we'll do 80%. So to figure out 80%, we basically take our 3000 number and, we're going to times it by 1.2. So if it's 80% efficient, we're going to need a 20% boost, right? So 3000 watts coming out of the inverter into our surge of our load. So if you're like starting a refrigerator or an air compressor or something, then that means we're going to have to be sucking 3000 watts out of the battery plus an extra 20% because of, the efficiencies, the connections, the inverter itself, yada, yada. So real easy. You just take 3000 times it by 1, so you have 3000 itself, and then 0.2 to add in the 20%, and that gives us 3600 watts. So And I know that might, go from 2000 to 3600 might sound kind of crazy, but my electric bike, it's a 500 watt motor, and yet it pulls about 720 at its max. And for the sake of safety, we said 2000, right? So we're going to keep over here to the side 2000 watts, and then 44.8, and then what was that? 2000, 44.8. So we'll take lowest. All right, cool. So 44 amps. So this is going to be like our max expected non-surge number. We're going to keep that for later. So now we have a new number because the 67 is obviously not enough anymore. So we need to figure out what this is now. So we're going to take our new surge. This is going to be surge plus, oh, that's the wrong color. It's going to be surge plus efficiency. So our surge plus efficiency divided by 44.8, and that'll be about 80 amps. So now we can figure out, well, there's our fuse size, and now we can figure out our number of cells in parallel size or sizing. So we know the main fuse now is going to be 80 amps. That's the worst case. If it ever goes above that, then something's wrong and we need to, blow the fuse and safety the system. So we would also take that number to figure out, the per cell fusing and things like that. So we're going to, keep this example common. So for the DIY Powerwall guys, I'm going to use a common 18650. So we'll say 2000 milliamp cells. So if we're using 2000 milliamp cells, I like to always convert to amp hours. So that equals 2 amp hours. And let's assume we want to not drain it past 1C. That way we're not abusing them too much. So 2 times 1 obviously is 2. So that means we're going to see 2 amps per cell. And that's going to be pretty easy. So we know if we have 80 amp maximum load and we never want the cells to go over 2 amp maximum, we need 40 cells in parallel. And and then if we're going to do over here, that's why I wrote this down, at 40 cells in parallel at 44 amps, that's like 1.1 or something. So normal max load, we'll see 1.1 amps a cell. So real gentle on the cells. So hopefully they last a long time. They can handle a lot of cycles. And each cell will only see 2 amps. So now we can come down here and figure this stuff out. So we already know the max, fuse, what the batteries need to have. And if you want to fuse in between your cell banks, that fuse right here needs to be the same as the big 80, because the same amount of power is going to flow, in and out to the load. That's going to flow between the cells. That's not really required. I don't recommend it, but if you want to do it, that's cool. The only time that's going to pop is if like this connection here touches this connection over here. And that shouldn't really happen. I know, like, for instance, in like boats, the batteries are like under the deck and you open a thing and you can see all the connectors. But, most of those should be covered. Those wires shouldn't touch each other. Now, the cell fusing I do recommend, especially with the lithium ion packs. And the reason for that is, for me, whenever I deal with a project that I'm unfamiliar with, I try to see what the pros are doing. So with Race Car World, I'm often looking for inspiration and ideas from Formula One. With lithium ion stuff, I look at like Tesla. How do they build their battery packs? Well, they use fused wire. All right, cool. So if they use it, why do they use it? Well, there's a really good reason, and that is if they're going to warranty a battery for 10 years, they want to make sure that it'll be resilient. And if you have, 14S, 40P, what is that? I don't know, like 700 cells or something, 400 and something cells, or 480 or whatever. 1% goes bad, that's 4 cells or 5 cells or something. So 1%, is going to fail in a couple of years. And when those cells fail, you don't want them to drag down their things. You're going to end up having your battery management always having to do balancing when you really well-built electric car like the EV West guys do. They almost never balance the cells out. But, these guys, might be using recycled, so the battery management will be working anyway. But, you really want that cell when it fails to be disconnected. And that's what the fuse can do. That's why I went on that giant tangent. We want these things to cut off and go away so they don't, we don't risk a fire or anything like that. And so we want that fuse, though, in that case to be very close to this max number. And quite literally, I would use that plus 10%. I would find something that pops at 2.2 amps. And that's double what you're expecting over here. So, it should only pop when the battery's going bad. And you could say maybe you want more cells in parallel, but 40 is pretty good, because you also have to think about when this project's done and cells fail, you don't want to have to check it all the time. You want it to be able to handle several failures. But 40 Ps, you got double here. So you could have, 10% of your cells fail, and it should operate, without too big of an issue. But yeah, so a quick review. So when you're figuring out the amps and the wattage and, your fuses, the wattage should be easy because the motor you're powering or the inverter you're running or whatever your load is, you should, kind of know your load. Whether you've tested with the multimeter or, a kilowatt meter, something like that. Most devices will have a rating on it. You can always start with that rating, find the surge rating, times it by 1.2 to add 20% onto it, or 1.3 to add 30, or 1.1 to add 10%. Decide on your lowest operating voltage. Where does the inverter cut out? Where's the motor controller cut out? And then you can take, that surge, divide it by your lowest operating voltage, and that'll give you, your worst case, current. And that is about where you want your fuse to be. You don't want to be too much bigger, because then there might be too much current through something and the fuse won't save. That fuse is that last line of defense. You want to save your system. And then from there you can figure out how many cells in parallel. Basically decide on what discharge rate you want to run. I like to always try to be conservative, especially on a device I expect to last for a few years. 1C on a 2000 amp pack, but maybe you've got LiPos, or maybe you've got lead acid batteries, and what you basically need to come up with is how many amps per how many amps per cell or battery you want to pull. Use that number, divide the worst case, divide it by the number of amps per cell or battery. That's going to give you your parallel, the number of cells you're going to need in parallel, like I have down here. And then from there, kind of keep in mind the expected usage number, so that if you want to fuse each cell or battery, you can know what about that fuse should be. And I do highly recommend fusing cells. It's kind of a maintenance thing as much as it is a defense mechanism. But I think that's it for now. I'll try to keep this short. If you have any ideas or questions, things I can help you try to understand, please let me know. Any comments, I enjoy feedback. Also, if you need me to clarify something, I do know I tend to talk fast and I'll go off topic because my brain's crazy. And like when I decided to write the purple letters down. But by all means, when you guys build your projects, try to write this stuff out. Make pieces of paper with all the numbers on it. It'll help for diagnosing. It'll help, when things go wrong, you'll be able to understand why, maybe. Let me know. Thank you for watching, and I'll see you on the social medias. Bye.